Hello Chem 1B, this is Chapter 18, Lecture Video 7, and we're going to continue talking about delta G naught. Specifically that it is a state function like delta H and internal energy, and actually delta S as well. And if you don't remember what that means from Chem 1A, it means that we can calculate it using a bunch of different methods and we'll still end up at the same number for the same system. So what this also means then is that we can use Hess's law to calculate delta G naught of reaction using our delta G naughts of formation. So these delta G naughts of formation, we can look them up and we can use this equation to solve for delta G naught. One of the things that's very important is this only works at standard state, i.e. only at 298 Kelvin. If you were trying to do it at like 400 Kelvin, then no dice, this wouldn't work. So if we wanted to do this for like the combustion of methane, we need to look up the delta G naughts of formation. We need to balance our chemical equation here. If you look at this equation, it's not currently balanced. We need a 2 here and a 2 there. Then if we look at our delta G naughts, remember that elements in their standard state, like O2 gas here, have a delta G naught of formation of 0. So I probably wouldn't provide that on a test, but I'd provide the other 3 numbers on an exam in a table, most likely. At this point, we can just kind of plug these values into our equation, products minus reactants, and solve. And this is a great way to calculate delta G naught using delta G naught of formation. It's a little bit less work because you don't have to calculate delta H and delta S for the reaction like in the previous equation. But again, that one only works for standard state. So let's do this again. So we want to calculate delta G naught at 400 Kelvin this time for the reaction below this guy using standard enthalpies of formation and the standard entropies of, for formation, standard molar entropies. And we're going to assume these don't change with temperature. Again, this is a big part. I wouldn't tell you most of pretty much all of this. Like, you just kind of need to know that whole paragraph. Because we're at 400, this means I can't use that equation we just used on the previous slide because that one only works at 298 Kelvin. So I need to look up the standard entropies and standard enthalpies for SO2, O2, and SO3 and calculate each one individually, right? So again, products minus reactants, but this time for delta H. I know this is my product, and I have 2 of them, and I can look up that value, negative 395.2 times 2, because of this 2 here in the reaction. That's the only product. So now let's do the sum of the reactants. Okay, well, we got SO2 here, times 2, again, because of that 2, times the delta H naught of formation. These 2 values we need to look up, or they would be given on a test or a quiz. And finally, we got O2, which is an element in standard state, so it's 0 for delta H naught of formation, and times 1, but whatever. 1 times 0 is 0. So that gives me my delta H of my reaction, which is something we learned how to do all this in Chem 1A. Now, something we learned that's pretty much the same but somewhat new is now we can calculate the standard entropy of formation or of the reaction, and it's going to be the same type of equation. This time, though, we have to use our standard molar entropies, our S naught values. So we got to look those up as well, right? So we're going to look up this value here, or it'd be given on a test. We need to multiply it by 2 again because there's a 2 there for SO3. That's our only product, so then we subtract off the reactants. Now we have 2 SO2s times the S naught for SO2 plus 1, again we got a 1 here, we don't show it, times the S naught for O2. This is important. Remember, elements in their standard state are 0 for delta H naught of formation and delta G naught of formation. They are not 0 for their S naught values, so we'd need to look up this S naught value for O2, or it'd be given. Again, this gives us this value. You need to mind your units here. This one is in kilojoules, this one's in joules. That's not going to work well if they are put into the same equation. But we do have this equation that we can now use to solve for delta G naught. We have the delta H we just calculated, the delta S we just calculated, and we are given T is going to be 400 Kelvin. So we can plug all those in. Again, make sure you're careful. Joules and kilojoules need to be put into the same units. And this is by far the most common mistake that students make. So again, here's my delta H, 400 Kelvin is my temperature. Here's my delta S, and this part here is just converting from kilojoules to joules, or sorry, from joules to kilojoules. And if you do this all out, you should get your delta G naught for about -120. At this point, you could be asked, hey, at this temperature, is this reaction spontaneous? And the answer is overwhelmingly yes. I can spell yes, I swear. This is a spontaneous reaction. All right, and the reason why it's spontaneous, just to make sure we're all good, we got this negative delta G. And anytime you have a negative delta G naught or delta G for any reaction, that's a spontaneous reaction. So this reaction is spontaneous at 400 Kelvin. We just calculated that. But what if we change the temperature? Maybe it won't be as spontaneous, or it might not be spontaneous at some point. Remember that delta G, when you have both a negative, both delta H and delta S are negative, it will have a temperature at which it will flip from being spontaneous to being non-spontaneous. In general, the larger your temperature here, the larger this whole term will be, right? And since it's negative here, that makes this guy positive, which will eventually bring down our delta, or sorry, bring up our delta G. Which in our case, not a good thing for spontaneity. So if we think about this, what will be delta G for 298 instead? Will it be more or less favored, right? So in other words, is our reaction more or less spontaneous? Well, we can do that calculation pretty easily, right? All we got to do now is, instead of put 400 Kelvin here, we just put 298, and that's it. And because we lowered temperature, delta G became more spontaneous. In other words, more favored. Well, if you have any questions, let me know. I gotta get out of that. It's a hard habit to break. So delta G is very useful for quite a few reasons, but one of the primary ones is that it provides us a way to determine how much work our system can do for us. So there is a relationship between delta G and maximum work, and that the max work that can be done by a system is really just equal to negative delta G. Delta G naught of a reaction, delta G of the reaction, doesn't matter. This is negative because of the fact that surroundings and system are always equal but opposite sign. Now, that is super useful. However, the maximum really only occurs for a purely reversible process, meaning that I can move backwards or forwards through the process and not lose any energy or substances. Now, in reality, there's no such thing as a reversible process. All real processes are irreversible. You're always going to lose something. You're always going to lose friction, energy through friction, or heat in the wire, or whatever. So you're never going to actually obtain the thermodynamic maximum. That doesn't mean it's not useful. It's incredibly useful. And the reason why is because if you think about it, just because I'm never going to obtain the perfectly max work that I could get, it gives me a pretty good estimate of the amount of work that's possible for my system to do. Maybe I won't get that exact number, but I'll probably get something slightly less than that, and that's useful to know as well. Now this is very useful, especially to engineers. You can kind of think of like, hey, I want to use this fuel for my engine. I know the max work this fuel could possibly ever do is this amount. Well, that tells me whether or not this might be a good fuel or not, in a lot of ways if I'm an engineer. So if you guys have any questions, as always, please let me know in email or my Zoom discussion sessions.